Okay, so welcome back, and now we're going to talk about implicit differentiation. So what is implicit differentiation? Well, let's figure out let's start with the explanation of what explicit equation is. What does it mean to have an equation defined explicitly versus implicitly? When we talk about the way a function is defined, we would say that a function is defined, for example, y is defined, or a function of y is defined explicitly in terms of x, meaning that we have something like this, that explicitly in terms of x means y is equal to this rule that is defined by the independent variable x. Okay? Now, if we want to talk about implicit not differentiation, but implicit, an equation defined implicitly, then we can look at this equation here and say, well, y minus x squared is equal to 1. So we would say in this case, y is defines the function. So this here, we would say y defines the function here implicitly. Okay? Explicitly here, because y is on one side of the equal sign and all the other variables are on the other side, and you only see x here. So this would be defined explicitly, and this would be defined implicitly. Okay? So in most discussions of math, if the dependent variable y is a function of the independent variable x, we express y in terms of x. Okay, and that's what we mean by explicitly. Okay, so it's defining y explicitly in terms of x. So on the other hand, if we have something like this, this is not, so the function y is not defined explicitly, right, in terms of x. So, but this would be implicitly, because this implicitly defines this function. Okay? So now, why is that important? Well, when we talk about implicit differentiation, it allows us to find slopes of tangent lines to curves that are clearly not functions. Okay? They obviously, fail the vertical line test. And so then what we're doing is we are using the idea that portions of y are functions that satisfy the given equation, but that y is not actually a function of x. Okay? So for example, if we use this function, or this equation rather, okay. So this is an implicit function, right? So we would say that this implicitly defines, well, you could define many different functions from this one, okay? So you could say that this is equal to y equals the square root of 25 minus x squared for what? Well, we could pick well, just this one, right? So we could say implicitly defines this, right? Or we could do a piecewise function. We could say y equals, and we could define it as the square root of 25 minus x squared. And we could say for x is less than 10, or it should be 0. And greater than negative 5. And we could say negative square root of 25 minus x squared. If x is less than 25 and greater than 0. Right? So again, we could define many different functions from this. Okay? Because this is not a function, because this is the equation of a square, the equation of a circle with a radius of 5. Okay? Oh, actually, that should be 5, not 25. Okay, that's it. So that's what we mean by implicit differentiation. So what we're going to do is to take the derivative of a function that is defined implicitly. What we're saying is we are not sure what y is. We don't. It's an unknown function. So in this case here, just because we have this, we know that y is a function of x, but we don't know what it is. And so that's where implicit differentiation comes in. Because again, it could be either one of these or another function. We just don't know. That's why we say it's an unknown function. Okay? This is when it's written like this, it's implicitly defining a function. Implicitly meaning we don't know what function it might be, but it represents some function of x. Okay, so now, how do we handle, right? So how do we handle this? So if we want to find the slope of a line tangent to the graph of x squared plus y squared equals 25, and let's say at a point 3, 4, we could evaluate the derivative of the function y equals the square root of 25 minus x squared, right here, at x equals 3. On the other hand, if we want the slope of the tangent line at this point 3, negative 4, we could use the derivative of the function of this one, right? We could do that. Okay, but here's the thing. It's not always easy to solve for a function defined implicitly by an equation. So that's where the technique of implicit differentiation is going to come in to help us. Okay? So what it does, it allows us to find the derivative of an implicitly defined function without ever solving for the function explicitly. Okay? So we're going to use Leibniz notation because what we're going to do is we're going to find dy dx using implicit differentiation. And then what we're going to do, before we do that, we're going to put together problem solving steps. Because what we're going to do is we're going to use dy dx to represent the derivative of y when y is defined implicitly. And then what we're going to do is solving for dy dx, because remember, dy dx is the same as y prime. And that's how we're going to solve these. Okay? So let's stop there. In the next section, we're going to go through the steps, and then we'll do some examples. And when I do the examples and I go through this, it'll make much more sense. But understand the concepts, because this does come up again in Calc 2. Well, definitely in Calc 2. Okay? So see you next time.